Hello everyone, it's an honor to be here to give the presentation of our research on IGARSS 2022. The topic is Feature and Output Consistent Training for Semi-supervised Building Footprint Generation. It consists of 5 parts, including Introduction, Method, Experiments, Results, Conclusion, and Outlook. The task of building footprint generation is to produce building footprint maps from remote sensing data. The generated building footprint maps are beneficial to numerous applications, such as identifying undocumented buildings and assessing building damage after natural hazards, or as preliminary information for 3D city modeling. Although for this task, there existing convolutional neural networks, CNNs, are able to deliver very promising results. There is still a challenge for extracting building footprints in large scale. This is the CNNs require large amount of annotated data to obtain strong supervisory information. However, manual annotation of reference data is a time-consuming process. In this regard, OpenStreetMap could be considered as a good source to obtain this kind of annotated data. However, it is still difficult to obtain enough annotated samples because of the incompleteness and incorrectness of the OpenStreetMap data. In this regard, we want to develop a method for the building footprint generation from remote sensing imagery, which can take advantage of large amount of unlabeled data and limit the need of labeled samples. Building footprint generation is considered the task of semantic segmentation in this research, and its goal is to solve pixel-level labeling problems. In semantic segmentation, it's very expensive and laborious to acquire a pixel-level label. So, a growing attention is drawn on the deep semi-supervised learning to take advantage of large amount of unlabeled data and to limit the need of labeled samples. The current dominant semi-supervised learning methods in deep learning are 3 types. The first is weakly supervised training, but it requires image level or region level labels. The second type is adversary training. It can use unlabeled data, however, it is very difficult to implement. The third type is consistent training. It has advantages on 2 aspects. On the one hand, it can use unlabeled data. On the other hand, it is very easy to implement. The state-of-the-art consistent training-based methods use a teacher-student framework. Specifically, a student model is used to label the examples, while a teacher model is applied to a interpreted version of this same sample. Afterward, the consistency is imposed between the outputs of 2 models to improve the performance of the student model. However, this method has 2 limitations. On the one hand, these methods ignore the rich information encoded in the feature maps and generate impose consistency only over the outputs of the models. On the other hand, they add perturbations over the raw input or encoder's output for all types of data, failing to take the characteristics of the target objects into consideration when selecting the optimal position to apply perturbations. Recently, the perceptual mechanism has achieved promising results for image reconstruction, and they make use of the extracted high-level feature maps to improve the network performance. So, inspired by it, we propose to impose consistency on both features and outputs for the training of unlabeled data, which is capable of fully harnessing information in deep features and output predictions. As shown in this flowchart, The proposed framework is composed of a shared encoder, a main decoder, and an auxiliary decoder. The segmentation network consists of the encoder and the main decoder, and is trained on the label set in a fully supervised manner. The auxiliary network consists of the encoder and auxiliary decoder, which is trained on the unlabeled examples by enforcing the consistency of both features and outputs between the main decoder and auxiliary decoder. The effectiveness of consistent training-based methods relies on the cluster assumption, which means that two samples belonging to the same cluster in the input distribution are likely to have the same label. In this case, the decision boundary should lie in the low-density regions. And the cluster assumption has inspired many recent consistent training-based methods for semi-supervised semantic segmentation, which propose to assign the perturbation on the raw input or encoder's output. In order to examine the cluster assumption, the local variations at the encoder depth d are measured between the value of each pixel and its local neighbors. And the local variations with high values depict the presence of low-density regions. And it can be observed that low-density regions are not aligned with the class boundaries at the encoder's input or encoder's output. By contrast, the class assumption is maintained at the intermediate layer, giving the class boundary with high average distance coincide with low-density regions. Based on the above observation and analysis, we propose an instruction to assign the perturbation, and the perturbation should be added to the feature representation at depth d within the encoder according to the spatial resolution of remote sensor imagery and the mean size of individual buildings in the study area. In order to investigate the effectiveness of our method, we use three datasets with different spatial resolutions, and which consist of planning dataset, matrix dataset, and inverse datasets. For the competitors, we select different semi-supervised learning methods. The first step is to select the best semantic segmentation model to be the backbone for the semi-supervised learning. In this regard, we first investigate the performance of different semantic segmentation networks for fully supervised learning, and we can say that efficient UNet has achieved relatively better results on three datasets. So we use efficient UNet as the backbone in the future semi-supervised learning. Then we split the training patches into two sets, which are label set and unlabeled set. The ratio of unlabeled set and with label set are set differently. And here we can say that the proposed method achieved the highest accuracy for different ratios. Also, we then evaluate the visual results on different data sets. We can say that the proposed method has less false alarms and less omitted detections. To conclude this research, we have two contributions of the proposed method. First, we propose a semi-supervised network for building footprint generation, and this topic is rarely investigated in the current literature, and our method can use a large amount of unlabeled data to improve the performance of a model. The second contribution is that our method integrates the consistent training of features and outputs into a unified objective function for an end-to-end network. And from the results, we can say the proposed method outperforms other competitors. And for more details, which can refer to our latest publication in the IEEE Transactions on geoscience and remote sensing. Thanks for listening.